So we started talking about matrix algebra last time. Try to ignore that flashing sign. It's something here. Okay. By algebra, we of course mean the basic operation. You know about addition, subtraction, multiplication, division, exponentiation, and composition. We said these are as you expect them to be. You just add component-wise. With respect to multiplication, we said we have to look at a long list of possibilities. If you have an ordinary number that by now we call it a scalar times a matrix, for example, if you have numbers say 2, you want to multiply with a matrix that has say A, B, C, D, E, F in it. This is still component wise. This is really shorthand for adding that matrix to itself, so you are just doubling each entry, and so it's not all that eventful. What we are very much interested in is a type of multiplication that is really a sum of a bunch of products. To introduce that, we said, well, let's take a look at total on sale of several items, different items at different prices. So if I am selling say apples and oranges and say pears, and I want to sell apples at $1 each and oranges at $2 and pears at $3, and I have 10 of these and say 11 of these and 12 of those. So these are the prices per item. So let's call this a vector of prices, and then I have an array of numbers of the items I am selling or buying. I want to define a meaningful notion of P times N. Well, in this case, pretty much the only meaningful thing you can do. So if I want the total that I have spent or I am getting as cash flow, it's going to be 1 times 10 plus $2. I'm selling 11 oranges and $3 for each of the pears. So the total that I am collecting is 10 plus say 22 plus 36. So I am making what, $68 total. So this is a particular form of handling P. In some fashion we are multiplying P with N to get T. So here's our T, $68 we collected. Here are vector of prices. Here are vector of numbers we sold. Now to do this properly, we need to adopt some notation. In different courses you have different kind of notation used. If these two vectors were like say in physics and you wanted to calculate the work, over there you use a notion of a dot product. So you, in that case, you say I'm taking this vector, I am dotting it with the second vector, and I get a number out of that. So we said last time, if you have force, which is a vector, we multiply it by displacement, which is another work vector, and we treat it in the same way as we do here. What we get out of it is the work that has been spent to apply that force in that duration. In linear algebra, we have a particular way of handling this gymnastics that you see here. We write this first vector here, so I will write 1, 2, 3, and the second one we turn it, if you wish, vertical. So write 10, 11, 12. Customarily, no notation is written here to indicate that you actually want to do a multiplication. So it's up to you want to write something or not. They just write them next to each other, and the result of this is going to be that number. Once we know how to multiply, so we are going to call this a row vector or a row matrix, and the second one is a column vector. And out comes a single number, which is going to be some scalar. Once we understand this type of multiplication, then general multiplication is going to be straightforward for us. We just apply this idea over and over again to each row and each column, and then we write the results in a location which is inherited from the location of the row that we had and location of the column we had. So some of the exercises we assigned from this section, let's just go ahead, take a look at some of these things. Say, so let's take a look at some examples. So problem 8, it says, suppose I have a matrix which is -1, 0, 2, 2, 1, 3, 3, 0, 0, and I have a matrix B which is 4, 0, -1, 3, 2, 0, 0, 2, -4. Now shortly we are going to give some examples where would such matrices come from, but you can imagine that you can have prices and numbers in various formats, and you're just multiplying them. You are getting different totals in various scenarios. So if I want to multiply, it says calculate AB and also later on BA. So how do we do that? So it all depends on how comfortable you feel about doing a lot of arithmetic. If you want to write on the side, if you want to write just in your head. So what do? We segment this into a bunch of rows, and the second one we break it up into a bunch of columns. Each row is going to multiply each column in that fashion, and the result, which is a scalar number, is going to be written in a location which inherits its row from this row, and it inherits its column from that column. So let's just go ahead and do this example. What do I get? So -4, 0 times anything, so I don't need to pay attention to that. 2 times 0, that's also 0. So luckily, the more zeros you have, the easier the life is going to be. -1 times 4, so I just have a -4. Why in this location? Because this is row 1, column 1. And then you repeat this. How many times do you have to repeat it? Well, depends on the size of this. In this case, 9 times, exactly as what you said. So you choose some kind of systematic pattern of doing it, either on the rows or in the columns. Every now and then, some matrices turn out to be special. You can kind of figure it all out in your head instead of slaving over a lot of detail. So in this case, you just go ahead to the next column. So what do I get now? This is -1 times 0, that is 0. 0 times 2, that is 0. 2 times 2, that's a 4, so I just write my 4 here. Versus the last column. Now, what do I get now? -1 times -1 is a 1. 0 times 0 is a 0. 2 times -4, so let's write it out so that we don't get plus 0 times 0 plus 2 times -4. So 1 and 0 and -8, so my total is what? -7, is that right? Now you just go ahead, do this to each of these rows, and then you'll be done. So I'll have 2, 1, 3. So I'm looking at this guy now. 2, 1, 3 times that. say 8 and 3 is 11, and 0 just stays at 11. Now I take a look at this one. 0, 2, 6. So my total is not what? That was 0 and a 2 and a 6. I'll have an 8. So why do I write it here? Because this is second row, second column. Now I'm going to have second row, third column. So I'll have minus 2 and then minus 12. So what is my total? Minus 14. Now we just go ahead, concentrate on this one, 300. Because I have these double zeros here, makes my life easy, because this just picks out the very first row. 3 times 4 is 12, and don't pay attention to anything else because they're multiplying by zeros. So I just get 12. So what do I get here? 0, and 3 times minus 1. So some of these tricks has to stay in your mind so that you quickly multiply. So if I have a row with one non-zero entry, that non-zero entry is going to multiply the corresponding row on the second matrix, and that's all that you are going to see here. So this first non-zero entry was right on the very first location. So it targets the very first row of the second matrix and triples all of them. Everybody else just stays put. So you have to practice a lot of things like that so that matrix multiplication becomes second nature and simple for you. Now, here the book is trying to teach you some facts about matrix multiplication, and one of the most fundamental and basic facts about it is that special situation with respect to AB and BA. What does it turn out to be? That if we multiply, chances are very high that AB has nothing to do with BA. Okay, that is something that comes as a big surprise in linear algebra, that if you pick two random matrices, first of all, if you could calculate AB, that is not a guarantee that you could actually calculate BA. Perhaps the sizes are incompatible. Even if you could, chances are very high that the two of them have nothing to do with each other. So either one side of this isn't defined, or even if both sides are defined, typically they turn out to be different from each other. Actually, that becomes a topic all by itself. In what circumstances would the matrix multiplication turn out to be commutative? Right now, we put that aside. We just go ahead, multiply, see what we get. If it confuses you as to what you're doing, you might want to write this one first, even though it's not necessary. I could go ahead, write B first, so I don't confuse myself on whose rows I'm picking and whose columns I'm picking. So here's my B, here's my A, so it's minus 1, 0, 2, 2, 1, 3, 3, 0, 0, and this time we are picking out these rows and multiplying them with these columns. So let's try. Minus 4, 0, minus 3. So what is my net so far? Minus 7. That by itself, proof enough that this is not going to be the same as that, because these entries are different. How about the next one? So I said take the first row times the second column. What would that be? 0. Because the location of zeros on them complement each other, and they just cancel each other out completely. First with the last column, so I'll get 8, and these two are in complementary position as those two. So what do I get now? Just an 8, is that right? Because 8 is 0 and another 0. So now we go to the second row, do the stuff with the second row. So what do I have in this case? I'll have minus 3 and a 6, excuse me, minus 3 and a 4. Is that right? So I have 1. Second one I multiply, I just end up doubling in this entry. Third one, 320, that is going to be a 6 and a 6. I make it 12. If you see any mistake, let me know. Last row, 0, 4, minus 12, so that makes a minus 8. And then on the next column, we just get a 2. On the last column, we have a 6. Is that right? So if you look at that matrix and that matrix, there is no reason to suspect that they came out of multiplying two matrices in the opposite order. So you see, there is no connection between the two of them. So you have to keep this in mind, that matrix multiplication is not commutative. We really needed a frowning face here, but that's all we got. That makes the topic hard, also makes it interesting. You cannot move things around. That kind of messes up a lot of stuff that you have learned in Algebra 1. For example, if you had picked out, say, a plus b squared, which simply means a plus b times a plus b, something that you learn in Algebra 1. What would you have done there? You would have said a times a, well, that is a squared. A times b, that's a times b. And then b times a, that is b times a. Then b times b, but b times b we abbreviate to b squared. If it was ordinary algebra, what would you have done to these guys? Yeah, say a squared plus 2ab plus b squared. But how about in linear algebra though? In linear algebra, that luxury is gone because you don't have this. You can use one of these guys for the other one. So you say everything stops here. This doesn't happen not in linear algebra. Not when a's and b's are matrices. If they were just numbers, fine, but not with matrices. So you have to keep in mind that all those power identities that you have, multiplication and such, you are making some implicit assumptions there. You have to undo those things when you are doing just plain algebra. So that was an example for multiplication. Now let's go ahead and take a look at we want to explain a matrix multiplication in terms of calculating the totals on a typical business. So here's an application that is mentioned in one of your problems in your homework and also in the text. Situation is an appliance store where they are selling refrigerators and freezers, and they are keeping the retail price and the dealer cost of each of these items. So we have refrigerators and we have freezers, and then we are looking at sale price, and we are looking at the dealer cost, and somebody is keeping track of these things in tables just like these matrices that we use. So it's going to be, here are some typical numbers. So sale price of a refrigerator is supposed to be $4.45, for a freezer is supposed to be $2.50. Presumably they are buying these things at $3.10 each, and these guys at $1.80 each. Then they are keeping track of how many of these gadgets they are selling. So in the second matrix, refrigerators are going to occupy the first row, freezers are going to occupy the next row, and then we are keeping track of how many of these things we have sold in each month. So we have January and February and March, and then we have how many of these things we sold. So here are some examples of, doesn't matter what numbers you had. So what could we be interested in? We could be interested in finding how much revenue we had for the sale of these things in the month of January. If I want to do that, so I'll have here are, let's call it the matrix C for cost or prices, or maybe I should use the letter P. Let me use the letter. That's fine. Here's a P. So various type of prices is recorded here, and we have numbers recorded in. So this is the matrix P. Here's a matrix N. When we multiply these two according to what we have learned, what is it that we are calculating really? So if I take this, multiply by that, what's the meaning of my activity? So this is how much I'm selling each refrigerator for, and this is how many refrigerators I sold. So I have 445 times 32, and then this is a sale price of a freezer, and I am selling 21 of them. What does that apply to? This is all situation in the month of January, and what is this? This is going to be my what you call revenue. Revenue is the cash you have collected. Is that right? And then you have, on a business, you have revenue, you have cost. How much did you pay out to get your warehouse filled up? So for each of these refrigerators, you paid $310 to get them. Well, you bought them, so it's still, this is 32. So I'll have 310 times 32 plus 180 that I paid for each of these freezers, and I bought 21 of them. So that's one way of doing the accounting for that month. And then you repeat the game for February and March. So you have similar thing to do in those other months. Then you have a matrix that shows your revenues versus your costs. Then you can do with this table whatever you want to do with that table. So the idea is that this type of multiplication that we do is not coming out of Mars or anything. It's just really meaningful in situations when you have really a bunch of apples and oranges, different components. You have components. Those components are associated with bunch of with their own numbers, and then you are trying to calculate some sort of a total for the whole thing. So you end up doing this kind of multiplication. Notice that it doesn't really work easily if you want to just multiply individually. Multiplying individually, there are ways of doing it, perhaps ways of making sense out of it, but not used all that much. Okay, now what we want to do is to go ahead and become a little bit more theoretical about this, describe matrix multiplication in a little bit more theoretical fashion. Just let's go step by step so that we don't suddenly jump in the deep section of the pool. Let's practice working the same thing with letters instead of numbers. So I take this matrix as A, B, C, D in it, and second one I just call it X, Y, Z, T in it, so they stand apart. And I ask that we multiply these two. First of all, we check to see that the number of columns on the first and number of rows on the second match, so you can actually do the multiplication. Or just visually check. A matches with X, B matches with Z, so nobody's left out. You don't want any wallflowers or anything, so you just have the complete matching of these things. So tell me, what's the very first entry that we are going to get? So AX, plus BZ. That is one single entity there. It's maybe you want to separate it by a comma from the next entity. So we take that. Now we are multiplying with that, guys. So what am I going to get? I'm going to get what? AY plus BT, and then CX plus DZ, and then CY plus DT. You have to kind of train your eye to go on rows and columns and match things, make totals and so on. Okay. Now, exact same thing could have been done if I wanted to use subscript notation. You remember subscript notation? We said if you have your first matrix called matrix A, you call this A11. You call this one A12. You call this one what? A21, and this one A22. For big matrices, that is a reasonable way of handling the situation. We cannot use really letters. Here we'll have B11, B12, B21, B22. Now we are going to do the same thing. It's just we have to keep track of things, be meticulous about subscripts, make sure we don't get lost in writing them. Let's see, a special pattern is going to show up. I'll have A11 times B11. So who are we multiplying? We are multiplying this fellow with that fellow. So we have who is the next entry? A12, is that right? B21. Next, I got first row with the second column, so I'll have A11, B12 plus A12, B22. Let's go to the second row, first column. So I'm going to have what? A21. What is it? I'm going to have B11 plus A22, B21. And then A21, B12, A22, B22. Okay, that's not all that exciting, but let's check to see, we can check these things to see if there is a pattern about the way these subscripts show up that we better have to make sure that we are on the right track. What do you see about all this jungle of indices that we see here? There's a pattern in all of them. As you go from one to the next, what do you notice about these indices? Look at them. The adjacent matrices, the adjacent indices are the same. Is that right? And the other ones go through the whole list of possibilities. So this is 1, 1, then 2, 2, 1, 1, 2, 2, 1, 1, 2, 2, 1, 1, 2, 2. For the entry that is sitting on the location 1, in location 1, 1, there is something about this that tells you that it is sitting in location 1, 1. This is 1, 1. Or, how about location 1, 2? Location 1, 2. This is 1. This is 2. This is 1. This is 2. Location 2, 1. This is always 2. This is 1. This is always 2. This is 1. Location 2, 2. This is 2, this is 2, this is 2, this is 2. The intermediate guys, they range through all the possibilities, and then the very first and last indicate where you are going to be finally sitting. Now that idea generalizes to multiplication of any two matrices. Doesn't have to be 2 by 2. So when you take a look at the example in the text, this is the very first example. That's how it shows up there. You have like A11 A12, and so on, all the way to A1n. Row I of a general matrix is targeted, so AI1, AI2, AI, excuse me. So if I have one gigantic matrix here and a second one, and I want to multiply them, we said we are aiming at a row of one and a column of the other. So second one, we are going to call it B's. So let's say we go as far as column P over here, and this has n columns, so this one has to have n rows. Now if I am targeting row I of this, I want to multiply by column J of this one. So let's go ahead and call that B. If this wants to be column J, what kind of subscript am I going to have? 1 and whatever column number it happens to be. Say we are calling it, say, number J. And next one is going to be row 2, still column J. And we go all the way down. This is going to be the last one. This is row N, column J. So I multiply these two. Now I'm going to get a huge mess. This was just 2 by 2. You can imagine what this one is going to be. So just so that we focus on one of them, I'm going to write the entry that's going to inherit its location from this row. That is, I'm going to be in row I and column J. So help me out with this multiplication. Just remember, this is just one item, but it's going to kind of foam up and take up so much space. So I'm going to try to squeeze it in one location. Like maybe I draw it in black, like. So this is one item of a large matrix. Who is the very first entry here? AI1 times B1J. Excellent. So first here multiplies the first over there. You notice we start with I, end up with J, and the middle guy is the same, 1, 1. Then on the same list of multiplication, we have to do the next guy. So who is that? A, I2, B2J, and we go down the line to hit the last one, which is AI1, and then it's BNJ. So this is the character of what comes out. So if I wanted to call this thing, all of it was matrix A, and this was, I wanted to call it B. And this guy, I care to call it C. I want to give a description on who is sitting on the entries of C. So I say C, the fellow who's sitting at the location IJ of it. Let me write this correctly. I had to use a lowercase c. So this fellow, this we are going to call it Cij. Capital letter, big letter C for the whole matrix, a single entry of it. We use the lowercase c. This is the fellow that is sitting in the row I, column J of it. This is, I just copy AI1, down the line until AIN, B, and J. So that is a formula, if you wish, for multiplying two matrices. Of course, you are rarely going to use the formula, but just in case you want to see it, or if later on you want to enter any of the courses where some programming is expected from you, want to do some computer programming, this is something that comes up. Now we are going to have a little bit of a shorthand for the right hand side. The shorthand, if you have taken your calculus 2, is going to be easy for you to follow. Cij, we notice the right hand side has a pattern. It's not just random numbers being added, but it is following a very rigid style. You say, okay, we can give a command to indicate what we are doing here. Well, what are we doing? We know. Yeah, excellent. We use a summation notation. Summation notation, when you want to give a command of adding of a bunch of stuff, you say sum. So this is the word sum. It stands for sum. Sigma, the word letter sigma stands that you want to do a summation. Well, what do you want to sum? These guys, all of them have A's and B's in them. First index of the first one is I. The last index of the second one is J. It's the middle guy that is changing. It's 1 and then 2 and then all the way, the last one is an N. So you need to use some sort of a running index. Running index, whatever letter you want to use, that's fine. Let me see what the book uses. What the book doesn't use anything. So let's just call that running index, let's call it, say, X. Who is X? Well, X first is 1, then it's 2, then all the way to N. So say X starts from 1, ends at N. So this guy is referred to as running index. And this is the start of that index, and that's the end of it. The formula is good conceptually, or if you want to do programming, that's exactly what you have to do. You have to create a sum that carries this out. Those of you who have taken your programming class, how do you carry out such summation? There's a special word that you use there to do that. Recursion or a loop, or you either use a for loop or a do loop or whatever, some sort of a concept of a loop you use there to, when you are piling things inside one big pile, processing stuff and throwing it in the pile, like you have to do one multiplication, like you have to do this multiplication and hold it, next multiplication and then add it to that, next multiplication, add it to that, and so on. When you want to do similar activities in programming, they call it a loop. You're going through a loop of doing the same thing over and over again and carrying something that you might call a subtotal until when you are all done, then you have your total. So that is the spirit of things that we are doing with respect to multiplication. We already said gave a warning about multiplication. We said we better keep in mind that A times B is different from what? From B times A. That gives us a bit of a pause as to, well, of all these rules that I have learned in algebra, which one of them are still okay and which one is it that I have to watch out for. Essentially, this one turns out to be the only thing that is not okay in linear algebra. Everything else that you have learned, those are still fine. That is, for example, with respect to addition, you don't have any such problem. You do have commutativity of addition. What else did you have in basic algebra? So associative property, you have A plus B plus C. If you have a bunch of matrices, you want to add them. Question turns out, what do you do first? And luckily, the answer turns out to be, well, it doesn't matter what you do first. What else you have? So commutativity of addition, you have associativity of addition. We said this one you don't have. But how about matrix multiplication? Suppose I have 3 matrices I want to multiply. What are my choices? I can do these guys first, then multiply with the A, or I can do these guys first, then I multiply with the C. It turns out that this is still valid, even though it's not obvious why so. It's going to take a while to show that. We do still have associativity property of multiplication. What else did we have in basic algebra. Well, we said something about multiplication of a number with a matrix, like we wanted to talk about 2a or 3a and so on. In that context, we call this a scalar, and this guy was a matrix. What if I'm doing those type of activities? Well, I could have something like this: one scalar plus another scalar, the whole thing multiplied by matrix. What do you think? There's another. What do you think about another way of doing the same thing, or getting the same result? AA plus BA. So these kind of things that you used to do in algebra, those are fine. If you have one scalar, you want to multiply that sum of two matrices, you can break it up. There is nothing wrong with that. What do you think is number 1 times the matrix? Well, it's just a matrix. We said there is a special matrix. It's called the zero matrix. So we have to be kind of careful with that because I have a hard time writing it. So this zero matrix. What is the property of zero matrix? Well, if I add it to any matrix, it doesn't make a difference. Is that right? Now, we have a notion of negative of a matrix. What's a negative of a matrix? It is a quantity that you get by multiplying minus a with the matrix. It has the property that if you take a matrix and it's negative and you add them to each other, what do you get? You get the zero matrix. So we can go on through the list of all of these things. Everything in algebra is still fine. The only thing you need to watch out for is a lack of commutativity in the case of multiplication. So keep reading on section 1.3. We are still going to spend one more day on this.